Many thanks for inviting me. It's great to be here. So what I want to talk about is this question. What is sort of the intellectual prehistory of computers and the internet? And of course, the overarching question is, can questions like that ever be meaningful and productive? Okay, so, but I'll give it a try. And I thought hard about it, and I found three major ones. One is sort of a cheat, obvious calculation. The second is AI. And the third is logic.
I'm sorry to interrupt. We can't hear the speaker.
Sure. You cannot hear me? Point your mic. Okay.
Now we can hear you better. Thank you.
Okay. So, and I'll tell you about all three. By calculation, I mean that any reasonably sophisticated civilization is essentially restricted by defined and restricted by calculation. You need calculation for many things like inventory, taxation, war, navigation, architecture, and all that. And in fact, in some sense, our civilization is the first one that is very aware of this restriction, okay, that we really depend on calculation. And the problem is that as with most, almost all ancient civilizations, calculation was very difficult because the number representation was very difficult. So how do you add numbers in Latin? And of course, it's painful to even think about multiplying them. Okay, so as you know, the greatest breakthrough in calculation ever had nothing to do with von Neumann or anything. It was the positional system, the decimal system, and the algorithms that it enabled. Here is this man, this great sage Al-Khwarizmi of the 9th century AD. He wrote in Persian. He lived in Baghdad, and apparently he was born in Uzbekistan. So his nationality in 3 countries. But that was really the main breakthrough. And once, I guess 7 centuries later, the positional system was introduced in Europe. It was a revolution almost as big, if not bigger, than typography. It enabled science and technology until, of course, the culmination of it all, the computer. And we'll come to that. So AI is the second undercurrent, sort of intellectual undercurrent that eventually culminated into the computer, I think. The dream of the intelligent machine, and it spans so many cultures. And I have here the golem of Prague, the chess-playing Turk of the 17th century, the hero of Alexandria, his pneumatic device for opening the gates of the temple right on the time of the sacrifice and all that. And of course, I have HAL from 2001: Space Odyssey. I hope you have seen this film. It's a great film. It's where HAL is sort of, in some sense, the most sympathetic, the most human of all, most sympathetic of all the heroes, of the protagonists of that film. Certainly much more human than the robotic person who does him in the end. Okay, so incidentally, this is a singularly sophisticated audience. But you will be surprised. It's very difficult to talk about AI today, even today, to a wide audience without getting the question about, Professor, aren't you frozen with fear that one day we are going to be ruled by computers? Okay, so by machines. And I think I have a good answer to that. Okay, I'll just let you read it. All right, so And the third important undercurrent is logic. And I don't mean, I don't say that it's a precursor of the computer. Logic is a precursor of the computer just because every chip has a ALU and of course, chips have transistors that act for NAND gates. But I mean in a very more subtle and deep way, which I'm going to tell you. Logic, of course, started with Aristotle about 4th century BC. And Aristotle, I mean, what is interesting in following the development of logic is to understand the tectonic shifts in the uses of logic. Aristotle and the ancients used logic as essentially a methodology for empirical science. Okay, so Aristotle used it as a tool. Okay, the Organum is his book on logic, and organum means tool in Latin. So Aristotle used it as a tool for formalizing what scientists, working scientists do, what they're thinking about, syllogisms. And here is an unsung hero, Chrysippus, of ancient logic. He was born in Cyprus. He was of Phoenician descent. He was at some point the leader of the Stoa, of the Athenian Stoa, of the Stoic philosophers. But what is quite unacknowledged is that apparently he completed Aristotle's work in brilliant ways. For example, he introduced what we would call today Boolean connectives, and or not an exclusive or, besides the implies that Aristotle had already introduced. So not much happened in logic for about 2,000 years after that. Okay, so until this man, Leibniz, great German philosopher, scientist, mathematician, conceived, this is the man who brought you both calculus and optimism. Okay, so Leibniz had this dream. Okay, and to his to his frustration, he never got to work on it. Even though he did work on logic, and sort of there are manuscripts of his posthumously discovered that do work out a lot of things that George Boole, the other man, discovered 200 years later. But Leibniz had this dream that to use logic in order to for decision making, I would call today. So whenever there is a serious matter to be decided on war, fortune, whatever, justice, he was thinking that maybe what we should do is collect all the facts of the table, and then intelligent people should sit around the table and say the magic incantation calculemus, which means let us compute. And after that, after a long calculation perhaps, the inescapable conclusion, the right decision would emerge, okay, from the data. Okay, so that was his dream. He never worked on it. But of course, under his influence, George Boole came up with his famous book, The Laws of Thought, where the first part of the book is the foundation of Boolean logic. The second part of the book is the foundation of probability, very interestingly. So Boole came up with the Boolean algebra and Boolean calculus, the propositional calculus. So then this brings us to the beginning, to the middle of the 19th century, and this was a very critical moment for mathematics. It was a very dark moment for mathematics. Mathematics was in a crisis, and of course, when we think of mathematics, we think of the paragon of stability and certainty and truth. So the opposite of crisis. But the truth is that there was crisis in mathematics in the middle of the 19th century, and one sort of the precursor of the crisis was in the beginning of the 19th century, people discovered non-Euclidean geometries, okay? And this was very destabilizing, okay? Because Euclidean geometry was the educated person's only acquaintance of mathematics, the most certain things they ever knew. And now to be told that the theorems of Euclid, okay, well, it depends on the axioms. You know, it may be true, may be false. Okay, we don't know. That was a big shock. That was a huge shock, and it really shook everybody's faith in mathematics. Immanuel Kant himself lambasted the non-Euclidean geometers. So he didn't get it. I mean, he thought that their geometry is wrong because. His argument was that geometry cannot be subjective. Geometry, our brain is embedded in geometry, okay? So you cannot, geometry is the only objective thing in the world, okay? And then, after the shock of the initial jolt of non-Euclidean geometries, you have Cantor's theorems about infinity. Cantor was an engineer, actually, who was interested in what we call today Fourier analysis. And pursuing this goal, he decided he had come to grips with the nature of the infinity. And infinity was, of course, something, every mathematician now and then dealt with infinity. But at Gauss himself had admonition, all mathematicians treated infinity sort of, through long sticks, okay? They never touched it, okay? Infinity was something that you write under the limit sign, okay? So, and you don't think about it anymore. But Cantor started to study infinity and dissect infinity. And in fact, he came up with those wonderful theorems that essentially say that there are many kinds of infinity. There is the vanilla infinity of the whole numbers, and then there is the greater infinity of the continuum, and then there are even greater infinities, okay? And this came as a tremendous shock for mathematicians. They could not refute Cantor's result, but they attacked them. They said that this is not mathematics, this is religion or magic, and this, mathematics, the whole of mathematics was thrown into crisis. In this crisis, this man, Gottlob Frege, decided, so a rather unknown German mathematician, decided to set it straight. And so what he did is before writing his magnum opus on what he wanted to do, he wanted to redo mathematics a la Euclid, to sort of, to start mathematics from the beginning and prove everything from very simple axioms. And all of mathematics, essentially arithmetic. And then he took some time first in order to define his logical language, and he did define. He came up with first-order logic or propositional or predicate calculus, and so he introduced quantifiers for all that exists. Okay, and this made logic much more appropriate for attacking the crisis in mathematics, okay, for settling the crisis in mathematics. And then he started writing his, took 20 years to complete his great work about the foundations of arithmetic. And then disaster struck that Bertrand Russell, who perhaps the greatest philosopher of that time, came up, of the 20th century. Then he was young, he was beginning, he was in his early 20s. He came up with a very disturbing paradox, okay, that showed that all of set theory and certainly Frege's axioms were in trouble. They were not sound. There was a terrible flaw in the foundations of the edifice that Frege was doing. And instead of sort of describing to you what happened, let's do some poetry. This is a poem by Zissimos Lorenzatos. Zissimos Lorenzatos is a Greek poet. He died a few years back. Actually, he died in the little town next to Athens that I call home when I'm in Greece. He in a parallel universe, Lorenzatos could be the greatest poet of a nice country, but he had a strange fate of being born Greek, and Greece had an incredible, embarrassing wealth of poetry in the 20th century. Okay, so Lorenzatos was, of course, a very respected poet and critic. In any event, he wrote this poem, which I translated, The Setback. Beware of systems grandiose, of mathematically strict causalities, as you are trying, stone by stone, to found the gold-woven tower of the logical, castle and fort immune to contradiction. Designed in 2 volumes, the foundational laws of arithmetic, or Grundgesetze der Arithmetik, in 1893, the first, 1903, the second, a life's work, hammer on chisel blows for years and years. So far, so good. But as Frege Gottlob was correcting, content, the printer's proof already of the second volume, one cursed logical paradox, one not admitting refutation, questioned by Russell, Bertrand, forced without delay the great thinker of Mecklenburg to add a last paragraph to his system. Show me a great thinker who would resist the truth, accepting the irreversible disaster. His foundations in ruin, his logic flawed, his work wasted, and his 2 volumes, imagine the colossal setback, odd load and ballast for the refuge cart. So, that was actually Russell's breakthrough in science. I mean, he was just up-and-coming philosopher, and suddenly he became the center of attention. Everybody knew about his work. When he was asked much later how he felt about his paradox, he very frankly confessed that he felt as a devoutly Catholic journalist would feel for exposing the doings of a wicked pope. Okay, so so Russell set out to correct the storm that he had created, and with his former teacher Albert Whitehead, they started writing the Principia Mathematica, a volume whose purpose was to redo Frege's work correctly this time. What happened is that they had planned to do it in a year. 10 years later, they were not done, and finally they ended publishing a 3-volume unfinished work, which famously took 162 pages to prove that 1 + 1 = 2. Right after Russell's essentially failure, even though, of course, we know that many great ideas of the 20th century, for example, the theory of types, came from that work. So the reason why I said that Russell was perhaps the greatest philosopher of the 20th century is this man, Ludwig Wittgenstein, who was Russell's student, he was obsessed with logic. He was obsessed with many things, but certainly with logic. In the end, he decided that logic is not worth it. I mean, he returned essentially to Leibniz's dream. He thought that the only use of logic would be as a scaffold for language, whose purpose is social interaction and communication of ideas. So throughout this time, the greatest mathematician of the time was David Hilbert, who for 30 years, since 1900 until 1930, he was sort of the leader of this effort, massive effort by essentially anybody in mathematics in Europe at the time, to found logic, to found mathematics on firm logical foundations. And he was not only the leader, he was the cheerleader. With, he was a man of immense energy and magnetic speaker. And his rallying cry was, we must know, we shall know, in mathematics there can be no ignoranibus. And of course, they tried and tried, and they were making progress for 30 years until that day, 1931, that a young recent PhD from the University of Vienna, the name of Kurt Gödel, proved the incompleteness theorem. Okay, so which essentially says that this dream is doomed, cannot be attained. There is no mathematical system that no sound and complete mathematical system that can encompass all of mathematics. Certainly not arithmetic, as you understand it with plus and times. This, of course, was a disaster. It was the end of the dream. So what is interesting is that, in some sense, this is the darkest moment of the story. But as it happens in thrillers, the darkest moment is when the beginning of the process that eventually will lead to the nice end, the good end. What happened basically is that after Gödel's proof, of course, the people who were trying, logicians who were trying to set mathematics on firm ground were devastated. But some mathematicians, wanted to, there was still one ray of hope. Okay, so Gödel proved that there are these theorems that have no proofs. Fine. Let's forget about those. Okay, how about the theorems that have proofs? Is there a chance that we are going to generate, we are going to come up with a machine that actually produces these proofs? Okay, you give it a theorem, gives you a proof. If the theorem has no proof, then maybe God knows what it will do. Okay, but if you give it a theorem that has a proof, it will give you that proof. And I don't think that anybody really believed that this was a possibility. Okay, that by Gödel's devastating message, they were all convinced, I think, that this is also impossible. Okay, but they had to prove it. Okay, to just do one better to Gödel. Okay, to basically become as famous as Gödel. And what happened is that strange things happened. Okay, that until then they used the term machine loosely. Okay, they were interested in algorithms. They were interested in processes. Hilbert talked about machine many times, all these 30 years. But this was the first time that they were about to prove that a machine does not exist. Okay, and the nature of mathematics is such that when you try to prove that something does not exist, this is the first time that you must seriously understand what it is. Okay, so what they did is for the first time, a lot of people, a lot of mathematicians around the globe, they decided to define what a machine is, and define they did. And the definition that was by far the most influential, I guess because it was the most graphic, frankly. Okay, so the most evocative, was Turing's, Alan Turing's. Great. He was then even younger than Gödel. He was in his early 20s, and he came up with a definition. In fact, his definition was blessed with an explicit trait that he called universality. Okay, there was universal computer. I mean, Google should be interested in that because the universal computer essentially says is an existence theorem about software. Okay, that software exists. Okay, that's what the universality says. Okay, that you don't need to build a different computer for different. I mean, different computer for doing your taxes, different computer for typesetting, different computer for browsing. Okay, you need one computer for everything, and then somebody will write software for it. Okay, that's what the universal machine is. And it may sound like, great ideas. They have the curse of sounding obvious 100 years later. Okay, but it was not obvious. Okay, it was not even the leading idea. There were these people like Howard Aiken at Harvard, who were saying, I mean, I'm quoting, from, I believe, from Howard Aiken, who said that if the same computer was built in order to do both ballistic calculations, so a scientific problem, and business calculations, I believe that this would be the greatest, either a mistake or the greatest coincidence in the history of science. So people were deeply convinced that you will need to build specialized machines for specialized applications. Okay, so the idea of universal computer was very novel, and at the time, I'm sure it appeared extremely wasteful. Okay, so so you have hardware, software for and I mean, I used the internet, the origin, the roots of computer and the internet. I mean, I used the internet in the title of my talk, not because I wanted to sound cool or or relevant to Google's business model. I mean, but I meant it very well. I mean, that this is the root of the internet in the following sense. Okay, universality. If you are not convinced yet, I mean, universality is the root of the internet. In the following, I mean, consider this: that television was invented in 1900. I don't know how many of you knew that, but in 1900 people had television. But 50 years later, nobody had television in their home because there was nothing to see. Okay, and the reason there was nothing to see is because there were no televisions. Okay, so nobody had the incentive to create content. Okay, so I mean, silly chicken and egg problems like that can cost you centuries. Okay, that's the point. Okay, but when the internet came about, okay, and people sort of came up with sort of a rudimentary web, sort of remote procedure called an FTP together. There were a million people who had little computers on their desks. Okay, and as a result, all these computers, because they were universal, they could also click, among many other things. Okay, and click they did. Okay, and that's how the internet became a reality within months. All right. So and to make a long story short, Turing, as you know, worked for the British intelligence during the Second World War and used his computational ideas in order to break the Nazi codes. But right after the war, he and most famously von Neumann built some real computers. And the rest, as they say, is history. Okay, so in this sense, I think that computers have logic at their roots. And what is, of course, I think very amazing is the dark and relentless human tragedy that engulfed all of these people. Okay, so I mean, where does one start? Okay, so Kurt Gödel, I don't know how many of you know that. I mean, but he died in the 70s out of paranoia. He refused nutrition, so he died. He basically starved himself to death. Georg Cantor, so the man who brought us infinity. He spent most of his life in mental hospitals with deep melancholy, so depression we would call it today. Perhaps the most tragic of all is Emil Post. He was a teacher at City College in New York. He was a professor, brilliant logician. He came up with essentially Gödel's theorem 10 years before Gödel. But out of pathological insecurity, he kept it in his desk. When Gödel came up with his proof, he showed him his results and became Gödel's greatest fan. And there is a very moving letter where Post tells Gödel, it's not the theorem doesn't matter. It's the person who essentially popularizes the theorem who deserves the credit. And he also came up with a machine, but they pressed him to this time publish it. Okay, so that's how we know about the Post machine. So he was manic depressive, and essentially he died in the hands of his doctor during electroshock treatment. in 1952. So even Russell and Hilbert, paragons of sanity. Russell feared madness all his life, and he had, for good reason. He had a schizophrenic son and 2 schizophrenic grandsons, and even Hilbert had a schizophrenic son. As for Frege, he was not insane. He was not psychotic in any way, except that towards the end of his life, he left behind writings, rambling writings in which he attacked everybody in sight, but mostly the Jews. But of course, this was completely normal in Germany at that time. Okay, so the only normal guy in all this, of course, was Turing. Okay, except that he was not legally normal. He was homosexual. I mean, Turing was 50 years ahead of his time in mathematics and science. He was 50 years ahead of his time in the way he lived, and he was very open about his homosexuality. And as a result, he was tried, and he was condemned to treatment by hormones, which changed his mind and his body. And as a result, he committed suicide, apparently, 2 years later. And this is the story we tell in the book, the Logicomix book. So I'll just take you through it. I mean, our narrator is, we see it from the point of view of Bertrand Russell. Okay, so this is the massive trauma that was Bertrand Russell's childhood. Okay, so I told you that Bertrand Russell was never insane. I mean, he lived to his 90s. And he became not only a philosopher, got a Nobel Prize in literature, mathematician, accomplished, educator. He became a peace activist towards the end of his life. But when he was, by the age of 5, he had lost. Tell me if you believe this. I mean, a father, a mother, his beloved older sister, and his house to fire, and then his only remaining loving relationship, which was his grandfather. So, but all this by the age of 5. It's amazing that he retained his sanity. Here is Russell discovering Euclidean proofs. Incidentally, I don't know if you noticed, but our publisher is Bloomsbury, and Bloomsbury is the same publisher who publishes Harry Potter. And of course, we had dreams of Harry Potterdom, because if you think about it, we are also talking about a British orphan who, at the age of 12, encounters magic. Okay, except that magic in this case is the magic of certainty that comes from a proof from the Book of Euclid. And he goes on to Cambridge, where he flirts with his future first wife. And does serious scientific work in white tie. And then goes on to a trip into Germany, where he meets Frege. And he also meets Cantor. This is the place where he went to meet Cantor. This is, if in the lower panel, you see, this is, if you're familiar with this metaphor, this is Hilbert's hotel, the Hilbert Hotel. Okay, so then he attends the first Congress of the Congress of Mathematics in Paris, where Hilbert gives his arousing speech declaring war on uncertainty. Then he decides to write the Principia Mathematica with Whitehead. He flirts with Whitehead's wife all along. Incidentally, the select few of you who have read my other novel, Turing, maybe you are wondering if there is a lot of sex in Logicomix, okay? So sadly, the only explicit sex scene that I could get past my puritanical authors is right here. It's the lower right panel where it involves two insects, okay? So, continues to flirt with Evelyn Whitehead. Meets with Wittgenstein. They had very tumultuous. Wittgenstein was a student, but of course he was the greatest student the man ever had, but also the most problematic. Of course, there is an interesting anecdote. That once Wittgenstein woke up in the middle of night, 3 a.m. Russell with philosophical subtlety, which he could let him sleep, and Russell told him, Ludwig, you are too intense. This is not going to be good. This is dangerous for your mental health. And Wittgenstein said, God preserve me from sanity. At which point Russell mumbled to himself, God most certainly will. Here you see Wittgenstein making his keep philosophical insight in the middle of the World War I battlefield, where he was reported to fight with suicidal courage. Here is Wittgenstein snowing Russell. Here is Kurt Gödel announcing his incompleteness theorem. All this during the rise of the Nazism in Austria and Germany. There is a framing narrative. We use a framing device where we have Russell give a talk in September 1939 to a unnamed United States university, even though I cunningly coerced the artists to make it look like Berkeley. Where his lecture is disrupted by isolationists, peace activists who want him to take a stand against the war. And Russell invites them to listen to his lecture about logic, okay? And because the implicit promise is that this will help us decide what is right. With this thin excuse, we give the story of logic. There is a second framing narrative. This time about it's the bunch of us in Athens when we work on the book. So this is a book about logic, mathematics, computer science, self-reference. Of course, you have to be self-referential. We go through both good parts and seedy parts of Athens during this, and there is actually a little adventure that we're having late at night. And the book ends where I think all books should end, which is in an ancient Greek theater during a performance of Oresteia. I'll be glad to give you to get your questions, but let me relieve you of the most obvious ones. Why? 5 months ago, in a bookstore in Baltimore, a kid asked me, "What were you smoking the day that you decided to write this as a graphic novel?" Okay, so here's the deal. No, not what, but here's what. When we started, I had no idea. I had only read Mouse. Okay, no other graphic novel. I was a complete ignoramus. Everybody else was a big fan. When Apostolos told me that, that his idea of writing as a graphic novel, sort of, you know, in the beginning, I laughed and then I cried, okay, when I realized that he was serious. But soon I was converted, okay, because so here is sort of a very simple reason why this is a good idea. This is basically an historical novel, okay? And if you think about it, historical novels, I'm not very fond of the genre, but historical novels have the following pitfall, that there is, you have to spend a lot of novelistic energy to define the atmosphere of the era, okay, to capture the period, okay? And in a graphic historical novel, you open the page and the period jumps out to you, okay? So, you know, so you can concentrate on plot and character, okay? So this is, to me, so, you know, so is it historically accurate, okay? No, it's not, you know, so, you know, there are several inaccuracies, and we have a page and a half in the end where we list them all, okay? So don't use it to learn history, okay? It's, you know, we are out to write a fascinating story, okay? That was our first goal, okay? And, nothing else. In fact, I mean, I gave a talk like this at Berkeley 6 months ago, and a colleague, so, you know, a philosopher who actually works on, you know, Paolo Mancosu, he very meticulously listed all the inaccuracies of the book, you know, and you know, and then I had to say something. I had to respond. So, you know, and I told him, but Paolo, Mark Antony never spoke at Caesar's funeral. Okay, so, you know, but we all know that he should have. Okay, so for example, Russell did go to Germany, but he did not meet Frege or Cantor. Okay, so these encounters we had to invent. So I hear, you know, a lot of people come and tell me, you know, Professor, I think I understood things that I never thought I would. Okay, but that really was not our goal. Okay, so, you know, frankly, there is too much education in my life. Okay, so, you know, I was here. I really wanted to write a book, to write a good story, and we had to explain some math, but in the same spirit in which, if this was a love story, you would have to stop and sort of describe the beauty of the beloved. Okay, so, you know, and it's in the same sense. I mean, you know, that what are these things that these great people are obsessed with? Okay, you have to say something. Okay, and that's what we did. Okay, so so this is so, you know, so this is my fear. So, you know, that Paolo Mancosu, sort of, you know, the philosopher I told you about. So, you know, he went through sort of, you know, a huge list of logicians and decided that only 6% are psychotic, which is sort of, you know, the average in the population. Okay, so so the answer is no, because logicians are not crazy, mathematicians are not crazy. Mathematicians, like all scientists, you know, have so, you know, they must concentrate, you know, for long periods of time to complicated things, you know, and that's why, so, you know, you have all these jokes about absent-mindedness and all that. I mean, you know, but I don't think they're, you know, they're not crazy more than, you know, more than they should be. Okay, and you know, so, but how, you know, still the great mystery remains. Okay, the amazing fact that out of the heroes of this story, a great majority had very serious brushes with insanity. Okay, so Peter asked me on the way here, so, you know, do I have a toy theory? And of course I have a toy theory. Okay, so the toy theory is this, that logic in the beginning of the 20th century had the promise of helping you. It's the tool to help you attain absolute certainty. Okay, so if you were a teenager at that time who was a brilliant mathematician, great in science, and at the same time you were very worried about what goes in your brain, okay, chances are that you would turn to logic. Okay, so, and that's what so many people did. Okay, that's again just toy theory. We talked about that. All right. So one of the greatest fun part, the most fun parts of this was to write copy for your own character. Okay. So this was great. I mean, and even more fun was writing dialogue for the other guy. Okay. So and we had many fights of the form. No, man. That's the line. My character is not saying this, okay? So, and we all lost a few of these battles, and I guess what I'm telling you is don't believe everything you read, okay? Okay. So, thanks a lot. Sure. Yes. There's also a call.
A little awkward. I know an anecdote or a rumor that seems to me to be a piece of this story, although a little later. But I've never been able to confirm it, and since you seem to know the story so well, I thought I'd toss it in there and see if you had heard it. When I was at Stanford, the story told of Paul Cohen, who was a teacher there at the time, and
he died recently. Yeah.
He finished the other half of Gödel's theorem, the independence half of the continuum hypothesis. And I'll point out just parenthetically that Paul Cohen, who I studied under, was not crazy or psychotic, but he was very difficult. But when he completed the independent side of the continuum hypothesis, he went to Princeton to see Gödel. And the rumor is, or the anecdote is, that when he showed the proof to Gödel, and Gödel, of course, at this point, was a hermit in his office who didn't come out for years at a time and was covered in papers, that when he showed him the proof of the independent side of the continuum hypothesis, Gödel said, yes, that's exactly the way I did it, too. And I wondered if you had ever heard that story, because it's very common where I come from.
I see. So I can tell you this. I had the privilege of sitting in the audience in 2006, 4 years ago, when in the Gödel Centennial in Vienna, where I heard Paul Cohen tell the story of his encounter with Gödel. And sort of, the year before and the years after. Certainly he did not say this. He did not mention this. Okay, Paul Cohen was the only other person in the audience at that centennial who had actually spoken to Gödel. I had spoken together, so I can tell you the story. I mean, I was a graduate student at Princeton and in the electrical engineering department, and I had a roommate, my office mate, who was sort of a horrible prankster. Okay, and in the tail end of a complicated prank that I don't want to get into, he left me a note saying sort of explaining the prank and then saying, if you have any questions, you can contact me in my Gödel number, and then he gave a number. So instead of factoring it, it was a 7-digit number. So I had a telephone there. So I thought it was his number. So I dialed it, and on the other side I hear a German gentleman. So obviously with German accent, older person say, "Hello." And I said, sorry, wrong number, and hung up immediately. So I have spoken to Kurt Gödel.
Thank you for coming. So I guess mathematicians in a way solve their problems with computers. Do you have any insight into whether physicists and M-theorists in particular are going to solve their problems with, like the Stanford with the linear, with, I'm sorry, not the linear, but the CERN accelerator, or Is anything happening there?
In computer, oh, I see. You always see with.
That theory.
I see. I see. You know, this is something that I know very little about. Okay, so you know, like everybody else, I watch and wonder. Yes. Yeah. So you know, but the first part of your statement about that mathematicians solve the problem with computer, I mean, is interesting. It's true that there is, you know, it's very true that there are very few mathematicians nowadays, or you know, who don't, in some sense, in some capacity, use computers.
So, I want to speak about a book that reminds of this Martin Davis one, the Universal Computer.
Oh, absolutely. Yeah. So thanks. Yeah. Yeah. So I believe in 1998, Martin Davis, who is sort of, you know, a great mathematician, logician, very much together, you know. So you know, he was at NYU. He spends now his time at Berkeley. Wrote a wonderful book, The Universal Computer, and I believe there was a second edition under different edges of logic. Yes, right. Yeah, which was essentially told the same story. Okay, you know, it starts from Leibniz and ended with von Neumann. Actually, I wrote an extensive review of this book. So you know, certainly it was one of the great inspirations for I mean, you know, I met, you know, we started writing this book, if you believe it, almost 9 years ago. Okay, so when we started writing it, I mean, you know, Martin's book was just out. And we had both read it, but I mean, you know, it did not. You know, we were not acquainted with the story through that book, but it rekindled our interest in the story. You know, so I met my co-author almost 9 years ago in Athens, and you know, at our first lunch, we started discussing this story. Not you know, a couple of months ago, actually, we started thinking about writing a book about it. But sort of our disagreement that sort of goes through the book, it happened during that lunch, and we sort of, you know, it was resolved during that lunch. You know, so that's. Sir.
Now historical questions. What do you consider, maybe from your theoretical computer scientist point of view, the most interesting, whatever it means, interesting open problems in logic now? So what are the most interesting problems?
The most interesting problems in logic. I mean, of course I have to mention P versus NP. So you know, which in some sense is the modern unsolved variant of Turing's seminal results. There are many wonderful problems problems in logic around P versus NP. For example, we don't know. You know, is there a second order sentence that describes graphs that are not Hamiltonian? Okay, so this is an important problem. So you know, it's a basic problem in expressibility in logic that would imply that P is not equal to NP. Interestingly, the continuum hypothesis is coming back to haunt us again. And sort of, you know, there is, you know, again, that's not close to my area, but sort of more than half a century after Paul Cohen seemed to get rid of it. So you know, there is mounting evidence that sort of that its independence is sort of not as consequential as we thought. Okay, that it's not really independent. Okay, that in subtle ways it may not be. Okay, interestingly, logic, as you know, sort of, you know, logic has, despite, you know, besides this stream of thought that directly led, I believe, to the computer, it has also it has also instrumented computers in very, very important ways. I mean, just to mention a couple of things. I mean, you have type theory in programming languages. You have logic in AI. You have glorious uses of logic in AI. You have logic in databases. Okay, so that's it has been really very much very useful. All right, I mean, it's during at least the 51st years of computer science, logic has been a great source of ideas and inspiration.
Are you working on another novel?
Am I working on another novel? Okay, so yes. Okay, so I am. I was. This is not the first talk about Logicomix I give today. Around before noon, I visited a wonderful school, Nueva School. It's south of San Francisco, and where the eighth graders had read Logicomix. So and they had questions for me, and I started sort of talking down to them, and soon, so I was on guard because these people were incredibly together. Okay, and one of them asked me, how has this writing this book changed you? Okay, so which, if you think about it, so is the question that you don't want to so this has writing a book is writing a novel. I mean, writing fiction is fantastically immersive. So when I first started writing a novel, it was 12 years ago. And at that time, I was a chairman of my department, and it's amazing that, but I knew that if I had to quit my job, I would have quit my job, because it was it was like a baby. It had to come out. I mean, otherwise it would kill me. This book was a little different because it was a little like subsistence farming. I mean, you work hard for 2 weeks and then you wait in hope for 6 months to see the chapter, okay? And then you work another, because, I mean, the reason it took us almost 9 years, if you open a page, every page is 2 days work by 4 people, okay? So this is and not the 4 people in the title page, by the 2 artists and 2 more artists, okay? So, I mean, so that's, and the authors just did the easy thing. I mean, we wrote some kind of script notation and then we interacted quickly with the artists, and then we let them do their work. So it was not as immersive, at least not for a long period. But right now, so every time I have to do something else, like teach or come to Google and talk, I have to shake everything else of my body because I live in a dreamland also now. Okay, so I'm more than half through it. Okay, so the title is Independence. It's not. It's only it has some connection to mathematics, not a very strong one. It's about Greek history, modern Greek history. It's a little about the War of Independence, but it's also about independence in the sense of probability. Okay, so. Yeah.